Hello, this is Professor Dan Kernler of Elgin Community College. This is another video in my statistics series. This one is all about how a variable is spread. All right, let's get to it. We're going to learn two measures of spread, and to illustrate these and develop the concepts, let's start with some fictitious exam scores. Got two sets here. The first set, here's a histogram, here's the second one. We can see that the means and medians are pretty similar, about the same, but if we look at the minimum and maximum on the first one, 38 to 99, the difference there is called the range. It's 61. Whereas with the second one, the range there is 53. So we could say that the first set is more spread out because it has a broader difference between the minimum and maximum. But that's not very precise because it only takes into consideration the lowest value and the highest value. Here's one that's a little more subtle. Again, here's some histograms, some fake exam scores. We can see that, again, they have very similar means and medians. The range here in this case is identical. However, this second set over here on the right is clearly more condensed. So we have to have another more sophisticated way to measure that. And we're going to take a few minutes here to develop this concept. It's a little abstract, but I'm hoping some visuals here can help you. We're going to start with some completion data from community colleges. This is a little outdated. I think it's 4 or 5 years old. This is the percent of incoming students that complete their certificate within 150% of the allotted time. So if they're getting an associate's degree, do they complete within 3 years? And here's some local community colleges. So the average is 21.2. And what we'd like to get is some kind of measure for how far the typical observation is from that mean. So let's go ahead and put the mean right in the middle. Try to get a visual. We'll put the different community colleges up. So COD is about 7.2% below that mean, ECC 5.8% above, etc. Here's the other three. So we kind of have a visual of how far they are from the mean. Let's focus just on the numbers here. One kind of initial attempt you might think is I'll just average these differences from the mean. The problem is some of them are negative, some of them are positive, so the average difference is just 0. What you could do is make them all positive. Think of a distance. The average distance from the mean is 5.4. That has meaning. That is actually a reasonable way to describe this. The challenge here, it's a little subtle, but when you're doing some of the inference later on in the semester, the absolute value is actually hard to analyze, and some of the theory behind it is more difficult, so we don't actually use this one for analysis later in the course. What we're going to do instead, and kind of be patient here and work with me, is what we're going to do for each of these is we're going to square that number. So the negative 7.2, we're going to square it and get 51.84. Think of that as the area of a square. And we'll do that for all the other four, and we get all of these squares. What we can do instead is find the average square, that's 30.64, and then take the square root to find the average side, and that's about 5.5%. Now, this seems like a lot of work to get a way to describe how far that typical one is from the mean, but the benefit of squaring and square root, if you've ever taken a calculus class, you're finding rates of change derivatives. It's easier to do that with squares than it is with absolute values. So that's kind of my subtle reasoning behind why we do this. Okay, so some terminology. The average square, where you add up all the squares and divide by the total, that's called the variance. And the average side length is called the standard deviation. Here's some formulas for those. So the variance, it looks a little crazy here, but the x sub I minus, that's just the difference from the mean. So you take the value, subtract the mean, square it. The sigma there means add them all up and then divide by the sum. Now, or divide by the total, excuse me. The n minus 1, I kind of have to wave my hands at that. It's a little subtle about why that's n minus 1 for the sample versus n. Now for a very large sample, a sample size 1,000, dividing by 1,000 versus dividing by 999 isn't going to make a big difference. But for small samples, what will happen is the sample is an estimate of the population. So you want the sample variance to be a good estimate of the population variance. if you divide that sample by the sample size, you end up underestimating the variance on average, subtly, by a little bit. So to be precise, you divide by n minus 1. There's a whole, remember, I wasn't able to prove this until I took a graduate course. We were doing all these moments and finding the expected value. Oh, it was fun. But that I wasn't able to understand it when I was in an introductory stats class. So unfortunately, you just kind of have to remember that for the sample standard deviation, for the sample variance, you're divided by n minus 1. And then the standard deviation, though, is just the square root of these. So we use, I forgot to mention the symbols. We use sigma squared for the population variance, and then s squared for the population, or the sample variance. You saw this with the means, where we had this Greek letter for the population parameter, and then a typical something from our alphabet for the sample. And so the population standard deviation is sigma, and then the sample standard deviation is s. And those are just the square roots of the variance. And again, to kind of remind you about the meaning behind this, the variances are the average square, and then the standard deviations are the average side length. Let's dive in and talk about some specific variables here and how we might understand this from looking at those variables. So let's look in our lesbian, gay, bisexual database. I'll put the link in the description. And one of the variables in there is life now. So we'll do a histogram. I've got a screen capture of me doing the histogram, and I think I'd like to do that and group it by race or ethnicity. Okay, I've got a couple up here, the one for Black or African American and the one for white. And we can see that they definitely look different. Not only is there a different peak for the two, but there's also a different spread. The white look a little more condensed. So let's look in StatCrunch and calculate the mean and standard deviation of these. So this is just like we were doing the mean and median. It's going to do summary stats, and then columns, and you pick your variable, in this case life now, and we're going to group by race or ethnicity. And what we find is for Black or African Americans, the mean is 6.1. For whites, it's 6.4, so it does, you can see that on the histogram, it looks a little bit higher. And then the spreads are different as well. The standard deviation for Black or African Americans is 2.0, and for white, it's a little bit smaller, it's 1.7. So again, the standard deviation is talking about how spread out that histogram is. It's not a huge difference here, but the white histogram is a little bit narrower, so it gives it a smaller standard deviation. Here's another one. This is from the Health Behaviors in School-Aged Children database. Again, I'll put that link in the description. I have the weight, the histogram of the weight, and it's grouped by the individual's thoughts on their body. So I have the much too thin up here and then the much too fat. So kind of both ends of the spectrum. And you would expect for those who feel they're much too thin to have a lower average weight, and for those who think they're much too fat to have a higher average weight, and you can clearly see that on the histograms. So the means are different, 93.3 versus 163.1, so this is as expected. There's also a difference in the spreads though. So the standard deviation for those who are much too thin is 29 pounds, and for those who are much too fat, it's actually very wide, and that's because there are some on the lower end that still feel they're much too fat, and then there are some at the very high end who are at over 200 pounds, and so there's a very wide range for those who feel that they are much too fat. So not only are the means different, but the spreads are different. Again, the standard deviation is about how far the typical observation is from the mean. It's about spread. And so the ones that are much too thin are more condensed than those who feel, not they are much too thin, they feel they're much too thin. So the ones who feel they're much too thin, because that's their own opinion, are more condensed than those who feel about themselves that they are much too fat. All right, one final concept thrown into this section. There are many variables that follow a bell-shaped curve, a distribution that's very symmetric, follows a bell-shaped curve. We'll talk a lot more about this in some later videos. But when they do that, you can actually say that the mean is going to be in the middle, and about 3 standard deviations will take you all the way to the outside. And with that, we can develop some approximate percentages, which is called the empirical rule. This is if it's this bell-shaped, nice curve that's symmetric, not a triangle, but it curves. So if variables follow a bell-shaped curve, we can follow this so-called empirical rule. And you can see along the x-axis, I have the mean in the middle, and then +1 standard deviation, +2 standard deviations, +3 standard deviations going out. So if a distribution follows this bell-shaped curve, then there's approximately 68% within 1 standard deviation, approximately 95% within 2 standard deviations, and almost everything, 99.7% within 3 standard deviations. Again, this is called the empirical rule, and this is only if your distribution follows that bell-shaped curve or is close to it. Then you could say, well, it's approximately those percentages, and those are within 1 standard deviation is 68%, 2 standard deviations 95%, 3 standard deviations 99.7%. All right, that is it for this video. Thank you so much for watching. If you'd like to see more of these, you can subscribe, hit the bell to get notified. This is part of a whole series. I also want to take a moment to thank the Elgin Community College Board of Trustees, which approved my sabbatical during the spring 2021 semester, and that's when I was able to record all of these videos. Thank you so much for watching. Hope you enjoyed it, and I will see you in the next one.